So, good morning all of you. Um, so, we have looked into the aspects of liquid flows in mini and micro channels. The major difference from the macro channel flow case is that some of the effects like the developing length becomes very important for the liquid flow in micro channels, and therefore, when you are calculating for example, the overall pressure drop, you should not jump into taking the fully developed condition and estimating the pressure drop. So, you also have to account for the developing section, and this is therefore, obtained through the way we define the apparent friction factor. So, the apparent friction factor now has two contributions, one from the fully developed friction factor and the other from the pressure drop in the developing region. So, if you are talking about lengths which are greater than the developing length, so this factor k of x becomes the Hagenbach factor k of infinity, that becomes a constant if your x is greater than LH. And having said that, so this how do we estimate the Hagenbach factor? So, that again depends on different cross sections, different aspect ratios. So, depending on that, the Hagenbach factor will be different. Okay. So, I have given you a very commonly used correlation by Steinke and Kandlikar to estimate the Hagenbach factor. This is a function of the ratio of A by B. So, I think if you go back, so that is the smaller dimension to the larger dimension A by B. So, if you take A by B as this is the inverse of aspect ratio, and if you put that into this correlation, this should give you the corresponding value of Hagenbach factor. And once you estimate the Hagenbach factor, therefore, the everything is known. So, we know k of infinity, we will know what is the friction factor for fully developed case. So, depending on again the different aspect ratios that you consider, the Poiseuille numbers are different. So, based on that you can estimate the friction factors, correct. So, therefore, this will give you the overall pressure drop for the micro channel, including the developing effects. So, apart from that, there are also some correlations like this form which is available, like Shaw and London for example have given a more explicit correlation in terms of x. You do not have to specifically take fully developing and add them separately. So, you directly have everything in terms of x. So, if you substitute the corresponding value of x, if your x is less than LH, it will give you a certain value. If your x is greater than LH, it will give you a certain value. So, if your x is greater than LH and if you are calculating the delta p for the entire tube length for example, so that will become a constant value. Okay. So, you substitute your x as L by d basically if you want to calculate the pressure drop for the entire length. Okay. So, then that becomes L by d by R e, which becomes a constant value, and therefore, this will give you the overall pressure drop for the entire micro channel. Okay. So, these are some of the commonly used methods of estimating the pressure drop for ducts with different cross sectional shapes, and so those are for the laminar flow. Now, if you move ahead to the turbulent flow case, again I have talked about the correlation by Phillips. So, he has correlated the F apparent as a function of the parameters A and B are functions of x by d. Okay. So, all you have to do is put in the value of x by d. If you are estimating the overall friction factor for the entire length of the tube, substitute x equal to L and you get a fixed value. Okay. Assuming that you have turbulent flow throughout the tube. Okay. So, this accounts for both the developing and developed regions of the turbulent flow. Okay. So, these are the two common methods for estimating the F apparent. Now, the other important difference when it comes to micro channel is the case of inlet and exit losses. I mean this is already there in macro channel case, but it becomes more apparent because the compared to the overall pressure drop within the channel, these losses can also be significant because you generally have very large plenums. Plenum widths are usually larger compared to the channel diameter, correct. The channel diameter is of the order of microns, the plenum diameter could be of the order of millimeters, and therefore, there is a large amount of constriction when it enters into these small diameter channels, and similarly the exit losses are also significant. There is lot of divergence of the flow, and not only that, you also can account for the pressure loss as it flows through the plenum, inlet and outlet plenum. If you put a differential pressure transmitter somewhere at this between this point and this point, so these 2 points, it should give you the overall pressure difference that includes also the exit and entry losses and also the bend. Okay. So, there is a sharp 90-degree bend in these micro channels, it is not smooth or rounded off. Okay. So, in these cases you also have to account for the bend losses. So, therefore, the overall pressure drop is apart from what you have already estimated for a single micro channel. Now, if you consider the plenum into picture, you also have to consider the inlet losses, the entry losses, exit losses. So, these are the contraction and expansion pressure losses and also the pressure loss due to the bend, 90-degree bend. So, therefore, we have the contribution of all of these in determining the overall delta P for a full micro channel assembly, that is with the plenum into picture. Okay. So, how do we estimate the entry losses, exit losses and bend losses? So, there are some standard charts available for circular tubes. For example, these losses are all plotted as charts. You can just refer to them depending on the contraction ratios, contraction area ratio and expansion area ratio. You can estimate the values of Kc, Ke, and you can substitute them. So, there are standard tables available. So, that is why I am not giving them here. If you take any fluid mechanics textbook, you should be able to find them out. Okay. So, therefore, if you are now substituting for F apparent in terms of F and the Hagenbach factor, you get a complete expression, right. So, therefore, if you are asked to calculate the overall pressure drop for a micro channel system, single micro channel system, you have to also account for the other contributions. So, we have I think done all this last time, and then we looked into the other important effect in micro channels, which is the roughness effect. So, all the previous discussion are all valid only for smooth channels, perfectly smooth channels, no roughness. So, you use the same correlations for the friction factor as the macro channel, same Pauli number and so on. But any practical micro channel, if you look at the surface profile, it is not smooth and definitely has a considerable roughness, and the roughness to diameter ratio, which is very important, will be quite significant in micro channels. The roughness itself will be of the order of few microns compared to the channel diameter of the order of few 100 microns. So, therefore, in the year 2005, Kandlikar defined certain parameters. One is basically what he defines as the average maximum profile peak height. So, that is we draw a floor or baseline, and then we estimate what is the average height of the roughness. So, that is the mean profile or mean line, from which we calculate what is the distance from the peak, and we take a simple arithmetic average of all these respective values, RP1, RP2, RP3 and so on, and that gives a kind of an average of the maximum profile peak height. So, that is RPM, and the value of FP, which is the displacement of this mean line from the floor is fixed. Okay. So, if you sum this value of RPM with FP, so that gives you the equivalent roughness. So, the overall roughness, since it is varying, it is not a constant value, it is varying with position. So, it is represented now by means of this equivalent roughness, which is basically the summation of the average maximum profile peak height and the distance of the mean profile from the base. Okay. So, now the good thing about defining this equivalent roughness is what Kanlikar did was he simply replaced the diameter which is there in all the correlations for friction factor, Nusselt number and so on, by what is called as the constricted diameter. Okay. So, that means the flow is now seeing not the full diameter, but because of the roughness it is seeing a reduced diameter, that is d minus 2 times epsilon. Okay. So, this equivalent roughness is useful in defining this constricted diameter, and now if you replot the Moody's diagram. Okay. So, that is if you take the circular tube, for example, for the laminar flow your F is equal to 64 by Re. Now, in terms of instead of diameter you replace everything with constricted flow diameter. So, it becomes 64 by Re based on Cf. That means, your velocity also gets modified, your velocity has to increase, okay, in order to satisfy mass conservation, and the diameter also is come down. So, therefore, the definition of Reynolds number based on constricted flow will be rho UMCF DHCF, where UMCF is calculated as m dot by ACF. So, based on this we plot the Moody's diagram, and all the micro channel the liquid flows in micro channels basically collapse onto these lines. Okay. So, very simple change in the definition of the diameter is sufficient to account for the roughness effects. Okay. So, although we are not really modeling all the individual roughness and how they interact with the flow, we are saying that the effect of the average roughness is to reduce the flow pathway. Okay. So, therefore, we just reduce the diameter using this particular simple relation, and then we find that this can predict the flow through rough micro channels very nicely. Okay. So, therefore, depending on the amount of roughness that you have, you basically calculate the constricted diameter, and for different values of roughness you can actually plot the Moody's modified Moody's chart. Okay. So, this is the simple modification with the constricted flow model. So, your relation is still the same, the Poiseuille number is still the same, only the definition of the Reynolds number is now based on the diameter of the constricted flow and velocity of the constricted flow. Okay. So, this is for the laminar case. So, similarly, the constricted flow model, there is a popular correlation. So, you can also use the standard correlations for turbulent flow and just use the constricted flow model diameter into that, but the one which is more commonly used was given by Haaland. So, this is a function of obviously the roughness to the constricted flow diameter. Okay. So, this correlation if you plug in the value of epsilon by DCF should give you the value of the constricted flow friction factor in the turbulent regime. Okay. So, now the kind of modified Moody's diagram has been found to be pretty good if you also look into the pitch between the roughness. So, that is how we are defining in an average pitch, that is we have SM1, SM2, SM3. So, we take an arithmetic average and call the mean spacing of profile irregularities, and it has been found that if you have a pitch to roughness ratio less than 5, the constricted model is able to predict well. So, this is usually used if if this satisfies this particular condition. For higher values you go back to the smooth channel condition. Okay. So, based on the lot of experimental studies which have been done, this kind of an empirical formulation has been arrived at. So, generally you first check what is the ratio of your pitch to the roughness height. Okay. So, if it is less than 5, then you use the constricted flow model, if it is greater than 5 you use the smooth flow model. Okay. Yeah. So, therefore, you can have different kinds of these roughness elements, and also the separation between them might also look different. For example, this is the smooth channel. Now, you can have roughness elements which are nicely spaced on the top and bottom, uniformly spaced, and if you calculate for example, the constricted flow width. So, it might come down, okay, for example. So, you might have a roughness element which is the equivalent roughness is 72.9 micron. So, accordingly your constricted flow width might come down. So, there are also cases where there is an offset, the top roughness is aligned in a different fray from the bottom roughness. So, in that case the constricted flow width is calculated based on the one at the bottom, for example, okay, and you can calculate the width, the constricted flow width as B minus the 72.9 micrometer. Okay. So, in the aligned case you are calculating BCF as B minus 2 times 72.9, because they are both aligned. So, you just use 2 times the roughness height to calculate the constricted flow diameter. In the case where you have an offset, you consider only one side, one roughness on one of the sides, whether it is bottom or the top, and then say just BCF is equal to B minus 72.9. Okay. So, based on this the definition of constricted flow diameter changes, and the other correlations are used as it is. All right. Now, just to show how their constricted flow theory predicts well with the experiments. Okay. So, now you have the fully developed friction factor. Okay. You have the laminar theory which is given by the solid line, okay, and you have the different kinds of profiles. You have aligned, you have the offset, and you use the constricted flow model. Okay. The constricted flow model shows completely a different profile compared to using the standard smooth diameter curve, which shows like this. Okay. And now, when you use the constricted flow theory, so the Moody's chart now gets modified and it matches very well with the experiment. Okay. So, this line here is basically coming from 64 by RE. If you use your normal diameter in that, you see there is a considerable offset between the experiment and the theory. Now, if you use 64 by RECF, you find that this line moves up and it agrees very closely with your particular experiments. So, this set is for the laminar, the other set is for turbulent. Once you go to turbulent flow, your friction factor increases. Okay. So, then you have to use the turbulent correlations appropriately. So, maybe you can use a correlation like this, and if you plot it, it should kind of come like these dotted lines here. So, this is the turbulent theory extended. Okay. So, therefore, the constricted flow model is been fairly accurate. We cannot say it is perfect model, but then it is a very simple model, but just by changing the definition of the diameter, you are able to match it very well with the experimental data. Yeah.
So, how big is the correction factor with respect to the diameter typically?
Correction factor in the sense?
So, the epsilon.
This epsilon is usually of the order of few microns, because this is the roughness height itself.
So, but the difference is very large because it is in log scale, right?
You mean here?
Yes, sir. The wire is in log scale, so it's like several multiples.
Yeah, this is in the log scale, you are right. So, if you are now looking at the definition of RECF, so two things are changing, not only the diameter, but also the velocity. Okay. So, you have to calculate what is the mass flow rate with the smooth channel, okay, and now with that you divide it by the constricted flow cross sectional area and you get the velocity. So, your velocity changes and your diameter also changes. So, then your RECF will change considerably. Okay. So, yeah, I mean you can do this as a calculation, I will give you a problem where you will calculate the F based on smooth diameter normal case, and then you use the constricted flow diameter and you see how much difference it comes out to be. And it again depends on the extent of roughness, for example, in this case you are talking about roughness height which is 72 micron, which is considerably very large. Okay, if your actual channel diameter is 200 microns and your constriction diameter now will be substantially small, right. So, therefore, this might make a big difference in the friction factor. So, it depends on purely the amount of surface roughness. Okay. So, the other important effect is that there is a transition that is happening from laminar to turbulent regime, and this roughness plays a very important role in the transition, right. So, if you have a smooth surface, then the transition will happen when your Reynolds number is of the order of 2300. So, that is the one which is quoted in literature for smooth channel. Okay. But if you have a considerable channel roughness, this Reynolds number can be reduced. So, for example, you look at the first correlation. So, if you put your roughness height as 0, you get your transition as 2300, which is your classical case. But for values of epsilon by d greater than 0, okay, you have values which are less than 2300. Okay. So, it will keep reducing progressively, and this is a kind of a linear reduction. Okay. So, therefore, the larger the value of epsilon, you have a considerable reduction in the Reynolds number where it becomes turbulent. And again there are two correlations here depending on the roughness height. Okay. If your roughness height is very large, again you do not want to use the first correlation, that might actually over predict the reduction in the Reynolds number for transition, and therefore, you switch to another correlation which will be more meaningful. And then if you use this criteria for and you plot the transition Reynolds number as a function of the roughness height, it has been found that this correlation matches very well with experiments conducted for both air and water. Okay. So, whether it is again air or water, so you have considerable effect of roughness on the transition, right, and therefore, you have to be careful how you define your transition criteria. So, if your roughness is quite large, you might actually talk about turbulent flows for channel size, the Reynolds numbers of the order of even 700 or 800. So, it is not very surprising that in micro channels you start seeing turbulent flows for small Reynolds numbers even of the order of 700, 800. Okay. In macro channels that is not common, right. So, these are some of the important differences. So, one is the effect of developing length, the entrance and exit losses. The other very important effect is the roughness, okay, which is often overlooked. For macro channels we do not even bother the roughness effects, we directly use the standard correlations for smooth channel, predict the friction factor, Nusselt number, and more or less it matches well with the experimental data. So, whenever we do experiments for tubes, circular tubes, we want to validate them. So, we validate only with the standard smooth tube correlation, but if you do same experiment with micro channel, you will find the values are quite off, your friction factor will be under predicted, your friction factor from experiment will be much higher than what you are predicting with your correlation. and the other is your Nusselt number, okay. The other is your transition. So, all this will be quite different because of the roughness effects, right. So, unless you account for the roughness properly, that means you make sure that you take into account the restricted flow constricted flow model, and you use the appropriate correlation based on the constricted flow model, then only it will match with your experimental data. Otherwise, your experiment will be on the higher side, as you see here, compared to the theory, okay. So, similarly the transition, many times we think that we are operating in the laminar regime, so at 700 800, but if your roughness is considerably large, you might be actually seeing turbulent flow in the micro channels, okay. So, therefore, these are some important aspects, although these are common to macro and micro channels, but these effects are more significant if you look at the micro channel case. Now, coming to the heat transfer. So far we were all focusing on pressure drop, friction factor, okay. So, these are the hydrodynamic characteristics. Now, your heat transfer characteristics are also similarly affected. Strictly speaking, if you have a smooth channel, then you can go ahead and use your standard Nusselt number correlations what you have derived for macro case. So, for the case of, for example, constant wall flux in the laminar regime, what is the fully developed Nusselt number? 4.36. If you look at constant wall temperature, 3.66. So, you can directly use that for micro channel also if it is 100% smooth laminar. Similarly, the turbulent correlations also are valid, okay. But what happens if you have roughness effect? So, then again you have to look at differences. So, for fully developed laminar flow, now we are talking about, when you are talking about these micro channels, another important thing is most of them do not have a circular cross section, okay, compared to the macro. In the case of macro ducts, you are talking about circular ducts which are commonly available machined, and you use these ducts with a circular cross section. But when you machine the micro channels, usually they are etched from a normal surface. So, when you etch them, you usually make a rectangular cross section, you do not etch them into a circular cross section, unless you are talking about capillary tubes, okay. Now, if you are talking about capillary tubes, they are glass tubes again. So, they are not very good for heat transfer. So, then you have to find copper tubes which are of the order of 100 microns, which is very difficult to make, okay, with a even profile and all that. So, usually whether you etch them with using lithography, photolithography is one option, okay. So, that is also done on a silicon wafer, and usually they are all rectangular cross section with different aspect ratios. Usually the aspect ratio is not 1. So, that is why all of these correlations are particularly emphasizing the use of different values of A by B, because most 90% of these micro channels have rectangular cross section with large aspect ratios, okay. So, otherwise we could simply use the standard circular cross sectional Poiseuille number and Nusselt number, but in this case, since the emphasis is on large aspect ratio rectangular cross section, so we rewrite everything. So, we may not be very familiar with all these correlations, but they have been developed for macro channel case from lot of experimental data. They have been derived as a function of the aspect ratio. So, for example, if you take the constant wall temperature case, once again depending on the value of AC, if your alpha C. So, if you put alpha C is equal to 1, so you will get your limiting case of square cross section, the fully developed square cross section. So, this you may not have done this in a theory course, because we generally cover either flow between two parallel plates, it is a 2D case, or flow through a duct, which is a circular cross section. But rectangular cross sections also have analytical solution possible, okay. And if you do this for different values of aspect ratios, you can actually build a correlation like this, So, this gives you the fully developed Nusselt number correlation as a function of alpha c, and similarly you have one for uniform heat flux. The uniform heat flux case should be always higher than the uniform wall temperature case. Okay. So, the same thing can be used for micro channel provided it is smooth. Okay. And you also have correlations for thermally developing flows. Now, these are fully developed both hydrodynamically and thermally. So, therefore, these are constant values of Nusselt numbers, right, for a given cross section aspect ratio and so on. But if you are talking about thermally developing flows, that means the thermal developing length has to be calculated. So, you calculated the hydrodynamic developing length as 0.05 times Re, right. So, now for calculating the thermally developing length, it has to be 0.05 times Re times Prandtl number. Okay. If your Prandtl number equal to 1, both the hydrodynamic boundary layers and thermal boundary layers grow simultaneously at the same rate. So, there is no problem. So, both developing lengths will be same. If your Prandtl number is larger than 1, your thermal boundary layer will grow faster and vice versa. Okay. So, and this 0.05 again you have to be careful, it is usually used for circular tubes. So, for rectangular tubes this value will be slightly larger. So, that means for circular tubes the thermal boundary layer length or hydrodynamic boundary layer length, developing length is shorter, whereas if you change the cross section to a rectangle, this now becomes slightly longer length. Okay. So, you have to be also aware of these changes in the constants. Okay. And then you can use your correlation like the Greitz correlation. The Greitz correlation is one of the standard correlations for developing flows, and for a circular tube this is given as a function of the non-dimensional position. So, at any non-dimensional position you can, in the developing region, you can estimate the value of Nusselt number. If you put your x star to infinity, okay. So, if you have very large values of x star, what happens? So, this second term would go to 0, okay. Then it goes to the Nusselt number for a fully developed region, that is a constant value of 4.36, close to that 4 point should be close to 4.36. Okay. This is for the circular tube. Again it depends on what kind of channel cross section. Most likely you may not have a circular tube, you may have a rectangular cross section. So, then you have to use the appropriate correlation for the developing flow for a rectangular cross section. Okay. So, you have to use some correlations available in the literature, where they have given some, based on lot of experiments, they have given an empirical curve fit for developing region for non-circular cross section. They are not so easy to find, but I mean you can make an approximation by assuming an equivalent circular hydraulic diameter and calculating it, if you do not find suitable correlation for rectangular channels. But for the developed case you have the analytical equation. So, there is no problem. Okay. Okay. So, therefore, I think to quickly summarize this problem, let us so now again you have for the turbulent regime, so again similar to the hydrodynamic problem where you had friction factor calculation for laminar and turbulent. Now, you have Nusselt number calculation for the fully developed laminar regime, developing laminar regime, and then you go to the turbulent regime. Okay. For developing turbulent regime you use these appropriate correlations, and for fully developed turbulent regime. So, this is the correlation by Nielinsky. So, these are standard correlations available for macro channel case, macro channel heat transfer for turbulent flows. So, this can be used for a wide range of Reynolds numbers. Okay. So, this is called the Nielinsky correlation, and good thing is they are plotted as a function of both Reynolds number as well as friction factor. So, depends on the cross section, your friction factor could be different. Okay. So, if you are talking about circular cross section, you have a different Poiseuille number, if you have a rectangular cross section. So, depending on the cross sectional shape, you can substitute the corresponding value of f and get the value of Nusselt number from this. So, it is not only particularly valid for circular cross section, but can be applied to tubes with different cross sectional areas and shapes. Okay. So, this however accounts for the increase in heat transfer only through f. Okay. That means, your f should be a function of the roughness height. So, if you know f as a function of roughness height, you substitute this and you get the equivalent change in the Nusselt number also as a function of the roughness. So, the roughness is implicitly there in terms of the friction factor, it is not explicitly into this particular correlation, but nevertheless this correlation has been found to be quite okay for predicting the micro channel case also. So, they have just used it, and again you have to be careful if you have a lot of roughness, you have to replace all this Re with Re constricted Reynolds number, okay, constricted flow Reynolds number. So, therefore, your f will also become FCF. So, f calculated based on constricted flow Reynolds number, and the Re here also will become ReCF, and accordingly your Nusselt number will also get modified. Okay, is that clear? So, this is basically looking, I mean in the case of Nusselt number, we have not developed anything specifically for micro channels. All of these correlations are already there for macro channel case that we have directly taken. Only that you have to be aware that, for example, if you are dealing with roughness, then you use the same concept of constricted flow Reynolds number into this correlation. So, whereas if you go to the laminar case, okay, so we have constant values here. Okay, so, this does not tell you what is the effect of roughness, for example, right. So, whatever Kandlikar's model is only limited to the friction factor prediction, the use of constricted flow Reynolds number, but when you go to heat transfer, we do not have a very satisfactory theory to account for the roughness onto the Nusselt number. So, we still use the same Nusselt number correlations as the macro channel case, okay, but if you really ask the question how the epsilon by d plays a role on Nusselt number. So, these correlations does not have any of those effects built in, but whereas for the at least the turbulent flow, you have the Nielinsky's correlation which implicitly accounts for the roughness. Okay. So, again there are some other effects which could be important, like for example, the conduction through the walls of the tube, the axial conduction through the walls of the tube. So, that is something which could be accounted for. The other is called the variable property effects. So, if you have variation in viscosity, for example, viscosity ratios could be very high, because the temperature at the wall could be quite different from the bulk temperature. Okay. So, in that case you apply some simple correction factors, that means you first assume a constant property and calculate the friction factor and Nusselt number, and then correct this for variable property by using some simple correction factors like this. So, once you know the constant property value, you get the variable property value by multiplying by this correction factor. Okay. So, these are again common to macro and micro channel case. Even in macro channels, our assumption of uniform or constant property is not accurate. So, very high, suppose you have very high heat fluxes. So, the wall temperature will be quite large compared to the bulk temperature. So, in that cases you correct your friction factor, because there is a variation because of the non-uniformity in the correction in the viscosity. So, you correct your friction factor and Nusselt number based on this, but these are all just empirical correlations. Okay. So I think yeah, so coming to the effect of roughness. So although there has not been properly correlated in textbooks, so some experiments have been conducted to understand the relative roughness effects. So you have 3 different roughness here, for example epsilon by d varying from 0.001 to 0.003, and then you plot the Nusselt number and you see that for the same Reynolds number larger the roughness, so you are higher the value of Nusselt number, right. So therefore roughness definitely plays a very important role, but you see all these have been plotted for the turbulent regime. So the Nielinski's correlation might be able to predict this well, but if you look at the laminar regime for values less than 1000, so there has not been very satisfactory approach to incorporate the roughness effects into microchannels. Okay. So definitely there is a considerable effect of roughness in the case of microchannels, both not only on the friction factor, but also into the Nusselt number. Okay. So experimentally it has been confirmed, only how much accurately we can consider this into the theory is not very clear for at least from Nusselt number point of view. For friction factor point of view, the constricted flow model seems to work reasonably all right. Okay. So with that, I think the theory behind the liquid flows in microchannels is complete. I just want to briefly go over some of the experiments we conducted in our lab with the microchannels in the next 5 minutes or so. So we have an interesting problem of electronic chip cooling. Okay. So we want to dissipate the heat that is arising from these microprocessors. So we have a chip packaging on which we want to mount a parallel microchannel system. So this is work of one of my MS students. So we have several of these microchannels in a parallel assembly, as you can see. Okay. So and you have an inlet manifold, you have an exit manifold, and you have all these pressure tappings to measure the pressure drop across the microchannels at different locations. Okay. So what we want to do in this study is, usually when you have a parallel microchannel system, the distribution of the flow is not uniform across all the channels. Okay. As you know that there is a pressure drop from the inlet to the from inlet to the end of this manifold, and this manifold pressure drop will result in a non-uniformity in the flow distribution through the channels. So we want to see how this is present in different types of microchannel configuration and how this affects the heat transfer, because the temperature also is going to be non-uniform because of this. So this was a study we carried out with 3 different configurations. So what you see here is we did a very clever design, that means we had only one microchannel system which simultaneously incorporates all these 3 designs. So we had to close, for example in the case of converting this, so this was the universal design that we had, and to convert this into a U type, we close the top and bottom and we open these sides, we close this side and this becomes a U type of microchannel system. Okay. The other Z type is we close this end and we close this end, we close the top and bottom, and this becomes a Z type microchannel. If you open the top and bottom and you close all the other ends, it becomes an I type of a microchannel. That means the flow comes like this from the inlet and then spreads across through all this. So I mean you can intuitively observe that in the case of I type, the maximum flow will be at the center, okay, and the minimum flow, so it will be a symmetric distribution about the center line. Whereas if you talk about the U type, you have, where is the maximum pressure drop? So you have the minimum pressure here, okay, and again you have a minimum pressure here. So you have the minimum pressure drop at this channel, whereas you have maximum pressure here, you have the lowest pressure here. So therefore the maximum pressure drop will be here. So you have the maximum flow for this channel and the least flow here, and vice versa for the Z type. So, therefore, we considered so we had a test rig and we measured the pressure difference in the first study. So, this was how we etched the micro channel system using photolithography in the MEMS lab, and so this is the procedure for making the mask and then etching process, and then we compared our results for pressure drop, and you see that we are able to agree for at least 88 micron channel. We had some models, theoretical models, which are available to estimate the pressure drop for a parallel micro channel system. It is not just one single micro channel. As a function of the channel number, we want to validate, and we got a good agreement, and we also modified the model which was already there, and we found that it agrees better. Okay. So, the thing is, there are two models, one which does not account for the pressure losses or viscous frictional losses through the manifold, and that is called the Bassoni and Martin model. So, which under predicts the pressure drop, and the other which actually does not account for the losses through the micro channels. So, that over predicts. So, therefore, it is important to consider both the pressure losses through the micro channel as well as through the manifold. So, we did this for different channel configurations, 100 microns, 178 and 352. So, apart from that, we also looked at the keeping the power input constant. We wanted to compare two different channel configurations, 88 micron, 176 micron, and see what is the effect of the flow maldistribution on temperature. And when you measure the average temperature and the maximum temperature, we find that between the 88 and 176 case, it makes considerable difference in the average and maximum temperatures. So, making the channel size smaller is beneficial in this case to reduce these hot spots. Okay. So, this is the important part of the study that we did, and again we looked at the influence of variable property. For example, if you have a power input, the properties are going to be different, and therefore, the flow maldistribution might be varying. So, therefore, we checked this as a function of power input, and we again see that it is a reasonably a strong function of the input power. Okay. At very low power, the maldistribution is somewhat reduced. So, all this is these are generally used for in the state of the art literature, when you want to incorporate micro channels into electronic cooling. So, you have to look at not just one single micro channel, but a parallel system of these channels, and you have to also simultaneously look at both the hydrodynamics and the temperature distribution. Okay. So, people are also looking at what is called the optimization problem. So, you want to optimize how many number of channels you need, what should be the diameter, and these effects and so on. Okay. So, with this we will conclude this discussion,